Today I will be speaking on data-driven models for designing metamaterials. So I'm a senior scientist with TCS Research, which is the corporate research division of the Tata Consultancy Services, TCS. Okay, a lot of members in the audience may not know that TCS actually has a very thriving research department. And the mandate of TCS Research is to explore emerging technologies to drive future capabilities and create impact for customers and society. So there are many research areas here, such as software systems, robotics and autonomous systems, embedded devices, physical sciences, life sciences, data and decision sciences, and so on. The common thread between all of them being that they intersect with computing sciences at some level. Okay. So there is a fair bit of optics that is also happening now within TCS, and it's primarily sensing for diverse applications, metrology, optical metrology techniques for defect detection. We do a lot of work with Tata Steel, for instance, imaging for quality monitoring, and so on. Okay, but today, of course, I will be focusing on just this aspect here, which is data-driven design models for electromagnetic materials. So the next few slides will attempt to give you a very basic high-level overview of the field of artificial intelligence, okay, which have led to revolutionary developments in many applications such as finance, manufacturing, retail, autonomous driving, and so on. Only a few have been listed here. And very simplistically put, artificial intelligence is used in situations where the tasks to be solved are too challenging for conventional programming. Okay. So the word task here denotes a piece of work that is allocated to an algorithm. An algorithm is often called the mathematical life force behind a model, right? So the overarching framework here is that the algorithm has to be taught to perform tasks, which it will do by learning. Okay, and learning itself is not a task, by the way. So we have also come across terms such as machine learning, deep learning, etc. I think it's very much all around us nowadays, and it always helps to have a clear picture of how they relate to each other, right? So artificial intelligence is nothing but the capability of a computer system to mimic human cognitive functions, and machine learning, or ML, provides the mathematical models of data to help a computer to learn, okay? And how are AI and ML connected? So basically, ML is what enables computers to become intelligent, okay? And use AI to think like a human. So basically, ML is a subset of AI, okay? And further, deep learning or neural networks, which is another term that we hear very often nowadays, is further a subdomain of machine learning. So it always helps to have this picture in mind, okay? So now the big question is, how does this really exciting, diverse field, relate to optics and photonics? What kind of new research ideas and developments can this intersection spawn? And the answer lies in the ability of artificial intelligence to address multidimensional, high complexity problems, okay, that are otherwise intractable with standard numerical and analytical techniques. So it's a great tool for interpretation of data, to do predictive modeling and automate process control, etc. And there are some excellent reviews that describe how AI has contributed to photonics. And if you're interested in this field, the students especially who are listening in today, I would urge you to read these reviews. So here are some areas where artificial intelligence and photonics have come together very successfully. So interestingly, AI and photonics are mutually beneficial, okay? Because machine learning techniques, which is a part of AI, as we have seen, adapt very nicely to problems in electromagnetics and phenomena that are dictated by Maxwell's equations. okay, as we shall see in the next few slides. So examples include, say, the engineering of artificial electromagnetic materials, which I will talk about. There's also material informatics for photonic materials, development of complex sources, field sources, etc. And additionally, optical systems also provide a platform for the implementation of AI methodologies. So for instance, there is now a great push towards finding new hardware architectures that have more similarity with how neural networks are structured, as opposed to conventional GPUs and CPUs, okay? So nanophotonic circuits and diffractive optical elements have been used for implementing the so-called photonic neural networks, okay? There's another term called photonic reservoir computing, which fundamentally models a neural network with randomized connections. Okay, so these are all very hot emerging fields. So let's talk about machine learning first, okay? So most machine learning algorithms can be classified on the basis of how the learning process is designed. So the most common form of ML is supervised learning, okay? Where the algorithm has to learn a mapping function from inputs X to outputs Y of a model, given a labeled set of input-output data pairs, okay? Where D is called the training set, and N is the number of training iterations that the model undergoes, okay? So the algorithm has to make predictions on novel inputs. And by novel inputs, I mean unseen data. And this process is called generalization or cross-validation. Now, when the output is a variable, a categorical variable or a nominal variable, such as a word, for instance, the problem is known as a classification or pattern recognition problem. Now, when Y is a real valued number, it's called a regression problem. Okay, so let's look at some examples of supervised learning in optics. So this is a paper that came out in 2018 from a group at MIT. And this work basically developed a model for predicting the scattering spectra and wavelength dependent scattering cross sections, of a spherical nanoparticle that is made up of alternating shells of silica and titanium dioxide of varying thicknesses. Okay, so this is a very complex nanoparticle. And the model that was developed was based on a neural network, which we will talk more about in a bit. And these are results of a forward computation to see how well it approximates the spectra that it was not trained on. Okay, so we see that the output, so the the output here, which is the red curve, matches the sharp peaks and the high Q features of the modeled spectra very well. So the red and the blue curves, they almost overlap here. So, the match is very good. So the results show that neural networks can be very powerful in approximating linear optical phenomena, such as scattering. Okay, so this is a case of supervised learning. Then there's also another type of learning called unsupervised learning. And this approach is based on unlabeled data sets. Okay, so essentially, an unsupervised algorithm receives only inputs D, okay, data inputs D, and the goal is to basically find interesting patterns in the data. So there's no guidance of a teacher or instructor. So there's no supervision on this data. Okay, so two typical examples are clustering the data into groups by similarity, as also reducing dimensionality to compress the data while maintaining its structure and usefulness. Okay, so there are other dimensionality reduction techniques, of course, like the principal component analysis and so on. But you can use unsupervised machine learning to do the same. Okay, so the application of unsupervised learning is as such broader than supervised learning. And it's actually, interestingly, much more characteristic of how humans think, because since we acquire our knowledge mainly through observation, we don't really, always have labeled data to learn from or explicit instructions. Okay. There's also something called as reinforcement learning, which I will not discuss here because it's not really used much in optics. So here's an example of unsupervised learning for an application in optics. So this is a very interesting generative model, this model over here, where the objective is to generate metamaterial unit cells or meta-atom patterns for user-defined spectra at the input. Okay, so the network architecture consists of three parts. Okay, there's the simulator, there's the generator, and the critic. And the simulator essentially solves the forward problem, or rather the direct problem, which is taking the metasurface pattern as the input and calculating the corresponding transmission spectra after being trained. The generator and the critic work together to generate metasurface patterns in response to an arbitrary optical spectra. So this is an example of a generative adversarial network, or a GAN, okay, which is a system where two networks compete with each other to converge on an optimal solution. Okay, so I think you know, a lot of you would have come across the term GANs now because they're very hot in other domains as well. So here's a unit cell of a metasurface which has a single layered gold pattern in a square lattice. So these are these patterns that were actually used for training the model. And the test patterns generated below by the model are depicted in here in black, and you see that the match between them is pretty great. So this is a very well-known paper again, which came out in 2018. Okay, so now we come to neural networks. Okay, so here I will not go into a lot of details because this is a huge field. Okay, so it is a very simple picture of what a neural network is and what it does. Okay, so deep learning uses artificial neural networks. You know, artificial neural networks, or just neural networks, are also sometimes called multi-layer perceptrons. It's also you know, it's all the same thing. Okay. And it is a type of machine learning, as we have seen earlier, where the world is seen as a hierarchical structure of concepts. Okay. So it's typically composed of a multi-layer structure of nodes. Here, this is a slightly complicated image, but hopefully we can go through it and understand a little bit of it. So these nodes learn and compute nonlinear input-output mappings. Okay, so you have the input layer here. Okay, where you know, you will have input data as a vector X, say, and an output layer which generates output data as a vector Y. Okay, and at least one hidden layer in between. So here you have, you know, many layers, but the simplest neural network will have at least one hidden layer in between the input and the output. So each circle in the diagram represents an artificial neuron, which is connected to other neurons in the neighboring layers by different weight values that are subject to learning. So in the forward inference, you know, when you start from the input layer, each neuron is connected to, each neuron Xi's here is connected to neuron Yj in the first hidden layer by a weight that is denoted by this term here, Wij. Okay. And it is then essential to apply a nonlinear activation function F, okay, to update the value of the neurons in the next layer. Okay. And this operation is repeated for all layers until you arrive at the final output layer, which gives the first estimate of the target response. Okay. Now, we'll talk about what your inputs would be and your outputs would be for a typical photonics problem in a bit. Okay. Now, the training process works in the reverse direction, where at each output neuron, a cost function is defined. Okay, think of a cost function as a fitness function. So here, the cost function here is denoted by C. And this cost function has to be minimized, and is minimized when the result of the forward inference is equal to the real answer. Okay. So the process of backpropagation, this is another term that you will come across a lot when you read about neural networks. Okay, captures how the error propagates through each layer by calculating the partial derivatives of the cost function with respect to the trained weights. Okay. So the weights are adjusted and scaled with respect to a factor called eta, which is the learning rate. I apologize, the slide is a little bit busy. And this process is repeated many times. So conventionally, the guiding principles for the design of photonic components, whether it be on a micron scale or a nanophotonic component or device, they're mostly designed through physical intuition. Okay, so which is based upon the study of simpler systems, or through experience obtained from previous practice and intuitive reasoning. Okay. So the optical properties of the initial design are usually computed by simulations that solve the Maxwell's equations. The standard, you have the Faraday's law, the Ampere's law, the constitutive relationships, and so on. So computational electromagnetics now, which was a field that came up a few decades back, can be classified into either frequency domain simulation or time domain simulation. Each category can be further classified now into either surface-based methods or volume-based methods. Now, surface-based methods have some limitations on applicability. And so over the years, volume-based methods have become more and more popular. Okay. And some examples of these volume-based methods are, finite difference method, finite volume method, the finite element method, FEM. Okay. Now, although and there's also the finite difference time domain method, of course. And although these methods are popular because of their simplicity, they don't really work well for complex geometries. And so the finite element method has become the sort of best choice for electromagnetics designers. Okay. Now, a given photonic design problem, okay, can be solved either directly, which was mentioned in the previous slide, right, where you solve your Maxwell's equations numerically or analytically, or inversely, where the basis of any strategy adopted is that the optical properties should be modeled with high enough accuracy. Okay. So a direct design process starts from first principles and relies heavily on intuition and experience, as I said. It doesn't really adequately sample the parameter space. So it is when you are sort of manually tackling a direct design problem, it is almost impossible for you to try out all the possible permutations and combinations and variations and so on, right? And therefore, it is quite tedious, it's quite time consuming, and it is computationally demanding as well. Now, inverse design here is an approach where the functionalities that you want, your desired photonic functionalities, which could be, reflection, absorption, grating efficiency, and so on, are obtained by optimization in the design parameter space. Okay. Now, this is based on a combination of advanced algorithms and also simulations. And the objective is to seek a solution that maximizes or minimizes the cost function that I spoke about earlier. Okay. So not just neural networks, any machine learning model also has a cost function associated with it, any other machine learning model. So some examples are listed here. There's a genetic algorithm, there's a swarm optimization algorithm, and so on. And real world examples benefit a lot from inverse methodologies because machine learning, and especially neural networks, enable one to automate and solve design problems in a much faster way than conventional optimization methods. Okay. And additionally, deep learning also allows one to tackle the direct and the inverse problem simultaneously. Okay, that's also something that is unique to neural networks. And this can help you to find complex, non-intuitive relationships between the structure and its optical response. So now we move on to an area where AI for on-demand design has been used extensively, especially over the last 3 years. So this is a very new and promising field for students who are looking for a juicy thesis problem to start working on, this is something that you could maybe look at. And this is the domain of engineered electromagnetic materials known as metamaterials. Okay. So this conference has seen several talks from renowned experts and stalwarts in the field of metamaterials, and I will not spend much time describing what they are, okay? But I'll just summarize some key points. So metamaterials and metasurfaces are, of course, composed of periodic subwavelength structures, which are called meta-atoms. They exhibit properties, electric and magnetic response properties that are not found in nature. Their properties are defined primarily by the geometries of their meta-atoms, as well as some functional material responses as well. And what is unique is, of course, it can mold incoming optical wavefronts at will. Okay. So traditional three-dimensional metamaterials. So here's a Lego visualization that I really like. So of course you have a single Lego block, which is now your meta-atom. And if you arrange it in 2D along X and Y, you have a 2D material. And then if you start to stack these layers one on top of the other along the Z direction, you get a 3D metamaterial. Okay. And 2D metamaterials are known as metasurfaces. And they typically have very thin dimensions, because of which their losses get reduced significantly. Okay. So here are some images of real metasurface devices that have been made for a diverse range of functionalities. Okay, so there's a large variety of geometries. You have discs, you have gratings, you have posts and pillars and so on. And so the point being that fabrication is complex. Fabrication is usually expensive because they're mostly lithographic processes that are used, especially for the optical and terahertz regimes. And any advances that can expedite this design process is of great help. So the question is now, can we have a data-driven rapid prototyping tool? And the answer is yes. And I spoke about this earlier, right? Artificial intelligence does a lot to automate and solve design problems in a much faster way. So here's a typical forward model, right? That's based on a neural network. So it takes in, what a forward model would do, as I said earlier, is it would take in design parameters, geometrical parameters of a meta-atom, such as the length, the width, the thickness, and so on. And it outputs the electromagnetic response, okay? Whereas the inverse model would take in the electromagnetic response, or the response that you want to design for, and it will generate the design parameters that are required for that spectra. So DNNs deep neural networks or artificial neural networks are also sometimes described as black boxes because it is almost impossible to extract an intuitive picture to explain how data is processed through these hidden layers that I showed you earlier. Okay, so there are some ongoing efforts for visualizing and interpreting deep learning models as well. Okay. Now, deep learning for inverse designs have been used with great promise. So this is not just, simulation only, people just sort of, build a model. There have been groups that have used neural network powered inverse models to give designs that they have then fabricated and tested and validated. Okay, especially for flat optical systems, metagratings, graphene-based metamaterials, and so on. Okay, so all of these materials have on-demand optical responses now. Okay. So now here we discuss a few challenges associated with deep learning for electromagnetic materials, primarily with the relationship between the design space and the response space. So this is a depiction of a one-to-one mapping scenario wherein a given response, EM response, can be obtained by only a single set of design parameters, right? So if your response is this vector Ri, then Di is the design which will give you that response. Now, unfortunately, this is not the case in many instances. And a more general picture is one where a given response may be described by more than one vector of design parameters. So here you have D1 and D2, which are two distinct designs that are still giving you an almost identical electromagnetic response. So this is a one-to-many mapping problem here. Okay. So in addition to that, there may also sometimes be no geometry which can give you the spectra that you want. A lot of the times, the mathematical models do not indicate if a valid solution exists at all as a consequence. And it also sometimes cannot provide a solution that most closely approximates the desired spectra. Okay, although there have been a lot of advances towards that kind of a model in the last, I would say, 18 months or so. Okay. Now, the other disadvantage has to do with the size of typical training data sets. You know, when you build a model, you have to train it. And when you train it, you have to train it with data that you generate yourself first. Okay. So early work in this area, the size of the training data was typically of the order of a few 100,000. You know, it can take you months to generate that kind of training data. So now we will go into some specific design case studies that we have investigated now at TCS Research. Okay, this is work done by myself and my colleagues. So this is an indicative workflow that can be used to optimally design a metamaterial. Okay, one begins by choosing what has to be designed, and then you go through steps to generate the training data set, like I mentioned. So you have to populate your database. And this is usually done by tweaking the design parameters, the thickness and the length and the width, and then recording its response, like the corresponding response, essentially. And then you have to store these design response pairs, okay? And the data is then processed or post-processed appropriately. You know, sometimes you have to filter out some unrealistic designs. Sometimes you have to do some sort of Gaussian smoothing to your spectra and so on. Okay. And then, of course, here, then finally, you have to design a cost function. Okay. That can determine whether the predicted response matches the actual response or not. And then you sort of iterate through this process till that cost function is minimized. Okay, and then you get your final result, and then you can proceed towards fabrication and testing. So our candidate design was a metamaterial thin film that was optimized for near unity absorption at around 1.6 terahertz. Okay, so what we want to test now is whether an AI accelerated framework, okay, a neural network powered model, can help design such a device. So the absorption here is achieved by arranging gold split ring resonators in a periodic array on a dielectric substrate. Okay, so split ring resonators, or SRRs, are a widely studied metamaterial element. I know that there have been talks before that have described this in detail. And they have permittivity and permeability values that can accommodate a wide range of practical devices such as filters, switches, modulators, and so on. Okay, so as the name suggests, it's a resonator. So it supports these inductive capacitive resonances, which arise primarily from the gaps in these resonators here. Okay. So this design was actually reported first in a paper way back in 2008. So we took this as our candidate design. And the absorber here is made of metal atoms that comprise two metallic layers, okay, on either side of an 8-micron thick polyimide spacer, okay, where the top layer contains the lattice of the meta-atoms, and the bottom layer is a 200 nanometer thick gold film. Okay. So this is a schematic of the individual meta-atom along with its dimensions. And the dimensions are defined chiefly by 4 parameters, namely the line width of the gold features, the thickness of the substrate, the length of the gold layer, and the width of the capacitor region. So we used a commercially available numerical package. We used COMSOL. So we use COMSOL for a lot of our work in this area to compute the full wave EM simulations for obtaining the spectral response, which, as I mentioned to you earlier, is optimized for near unity at 1.6 terahertz. Okay. So here are some more details of the training set now, just to give you an idea of how the model is trained. We performed a total of 5,200 simulations here, I think, yes, 5,200 simulations. And out of which some simulations had to be thrown away because they were not giving us realistic performance. And then this data set was further split into your test set, a training set, and a validation set. Okay. So how you generate this database is, of course, as I mentioned earlier, you would have to start to absorb, tweak and adjust the values of each of the parameters that I mentioned to you earlier. So 5,200 is actually not bad. It didn't take us that long to generate these number of simulations. So more details of this work are in the paper we recently published, which is shown here. It came out in Scientific Reports maybe 2 months back. Yeah. So this is the architecture, and this is the architecture which we call MetaNETs. Okay. And the MetaNETs architecture captures both a forward as well as an inverse model. So the forward model is a combination of a neural network and what is known as an LSTM network, which is a long short-term memory network. I'll describe it more in the next slide, where the inputs comprise of geometrical features, the 4 parameters that I showed you earlier. Now the DNN has 2 hidden layers, so it's not a very deep neural network. A very deep neural network means you have many, many hidden layers in between, okay? And once this model was trained, it was connected to the inverse model. And that's why you see this interesting thing. So what this network does, and this is called a tandem network, is it takes in spectra at the input, generates your dimensions here in the bottleneck, and it outputs spectra again at the output. Okay, so it's a very unusual model. So we have something called an encoder and a decoder, okay, which together form the tandem network. So the general schematic of an encoder, decoder, or together they're called an autoencoder, is shown here. So it's basically a multi-layer neural network that encodes high-dimensional data into low-dimensional data using the encoder part. And then the decoder decodes and recovers the high-dimensional data again, okay? And this layer here, which has the lowest number of neurons, is known as the bottleneck of the model, of the autoencoder. And it represents the dimension of the reduced space, right? So you're reducing the dimensionality and then recovering it again. So here we treat the absorption spectra as a sequential input. So this is very important here. In a normal neural network, your spectral values can be taken in a random order, and the model will still calculate something for you. But for this particular model to work well, you have to treat it as a sequence. So one, as an ordered sequence, and you cannot mix up that order. Okay, so within the encoder, the neural network transforms the output into dimensions, and then the network is forced to learn the geometry by applying the loss function or a cost function to the architecture. Now, before we explain what LSTMs are, which is what I showed you earlier, let's discuss what a recurrent neural network is. So it's called RNN. It stands for Recurrent Neural Networks. And it's a type of neural network that deals with sequence data. Okay, for example, words in a sequence, in a sentence. So a lot of your AI assistants, your Siris and Cortanas and Alexas or whatever, they use RNNs to a large extent. And RNNs have this problem that they suffer from short-term memory, which basically means that when information is propagated from the input layer to the output layer, sometimes very important bits and pieces get lost in the propagation. Okay, so this is a problem for long sequences. So an electromagnetic spectra with, let's say, 300 or 400 odd points would be considered a long sequence as well. Okay. In addition, during backpropagation, which is how the neuron values are adjusted, RNNs suffer from what is known as the vanishing gradient problem. Okay. So if you remember that slide that I showed you about the neural networks, you would see that there was this term called a weight, which was being updated through partial derivatives, right? Or gradients. So gradients are values that are used to update these weights. So the vanishing gradient problem occurs when the gradient shrinks as it propagates through time. And if a gradient becomes, this is the expression here, right? So if a gradient becomes extremely small, then there's no updation, right? I mean, the values of the neurons are not getting updated. So basically the model stops learning at some point of time. Now this is overcome by long short-term memory networks, which have internal gates that address these memory issues and regulate the flow of information. So these gates basically learn which data in a sequence is important and which can be thrown away. Okay. So like I said, you have a choice here, to either treat your spectrum values as a randomly ordered sequence, randomly ordered set of numbers, or you treat it as a sequence. And so if you treat it as randomly ordered numbers and you use a standard, you just, brute force apply a neural network and try to model it, it will generate something for you. So these results at the top here show what the ground truth is, which is the black curve. And then what the model generated spectra is, which is the green curve. And you see that the agreement is not very good. And there's a good bit of overfitting and so on. Whereas if you, when we sort of adopted the approach that I just described earlier with the LSTMs, the recurrent neural networks, we see that the agreement is much better. Okay, so it actually gave us very good agreement between what was expected and what was generated. So on the right here, we have results from the inverse model, where we randomly selected spectra, okay? And we made our model predict the design parameters that would yield that spectra, okay? So here's the inverse model, where you're starting from the response space and going into the design space. And you can validate this by, again, using COMSOL to plot the electromagnetic response of the designs that are predicted by a model. And we see that the agreement here was pretty good. So all in all, the model did very well. So here are some numbers which demonstrate how much faster a data-driven approach is as compared to calculations using, first principles. So, if you look at this red box here, this is the time taken, 0.5 seconds or so, for nearly 463 simulations total of these different absorber designs. Okay, whereas if you use COMSOL on the same kind of compute platform, you take about 54 hours if you didn't stop working, essentially. So 0.5 seconds versus 54 hours. Okay, this is the advantage that a trained model gives you. So here's a second design study that I will describe now, very briefly. I think I have about, I seem to have about 15 minutes left in this talk. So very briefly, I'll discuss a very new concept that has been developed for tackling problems in the physical sciences space. Okay. This is a work that was that we will be reporting in the near future at one of the premier conferences for neural information processing systems. So we will be presenting this 2 weeks from now. So if there's any one of you who's attending that conference, it's called NeurIPS. You will, hopefully stop by and see this work. Okay. So physics-informed models. Okay, so this is called a physics-informed neural network model. Physics-informed models seamlessly integrate data in mathematical physics problems. And these pins, okay, physics-informed neural networks are pins, are trained to solve learning tasks while respecting any given laws of physics that can be described by partial differential equations. Okay, so the PIN framework has been used with much success to classical problems in fluids, in quantum mechanics, in reaction diffusion systems, and so on. And they have turned out to be very data efficient models. So the number of training data set now reduces even more, because what is unique here is that the cost function that I mentioned earlier, I think, yeah, is now modified to a form where the standard mean squared error loss is now clubbed with a physics-informed loss, such that the partial differential equation that you're trying to solve, okay, so here this is a neural network that is attempting to solve a partial differential equation. And the partial differential equation that you're now trying to solve is embedded into the loss function, okay, using automated differentiation. And what happens is that, as I mentioned, it becomes a very data efficient model, okay, whilst still giving you high accuracy. It does not compromise on the accuracy at all. Okay, so how is this framework implemented for phenomena governed by Maxwell's equations? So the end goal here is to predict the permittivity distribution of a finite-sized cluster of scatterers that yield the same field distribution of the forward scattering calculation, and therefore effectively homogenize a metamaterial, right? So metamaterial is made up of meta-atoms, which you can kind of view as inclusions in a composite. And there is this effective medium theory, which approximates complex electromagnetic materials' effective permittivity and permeability. So here it would be a metamaterial's permittivity in terms of the permittivities and volume fractions of its constituent components. Okay. So essentially, electric fields scattered by a metamaterial are identical to those scattered by a hypothetical continuous medium with the same effective material properties, right? That is what homogenization means. Now, can you use this PIN framework to do your homogenization? And yes, the answer is yes, it has been done. The first few papers came out just about a year back. And it has been applied for very simple meta-atoms such as disks and cylinders, and all the way up to cloaking devices in the microwave region. Okay, so people have been able to design these cloaks using the PIN framework. Okay, I'll just go back here and mention a few of the advantages. Apart from the data efficiency, it also restricts the space of admissible solutions, okay, because you are now enforcing the validity of a differential equation as well. Okay, so you don't have to sort of aimlessly search through a large parameter space. You are now narrowing your search field. Okay, and it does not require any data on inverse parameters as well. So here's an architecture. This is an architecture that we developed that we have used to apply this framework. So it's a very simple neural network, nothing fancy, no recurrent networks, no encoders, nothing of that sort. But now the loss that this model is trained on is based on the Helmholtz wave equation, okay, instead of just a very simple root mean square kind of formulation. And this is what we designed. So here now, for exemplifying how this model performs, we computed the scattered fields for a relatively complex meta-atom, okay, which was essentially an aluminum circular split ring resonator on a silicon substrate, as shown here. And we see that we are able to replicate the resonance behavior of the meta-atom to a very, to a good extent. Okay, so you see this is the ground truth, and you see this field enhancement at the gap. Our model also predicts this field enhancement. However, there is a shift in the resonance frequency, okay? We had designed this for resonance at around 0.2 gigahertz, but then our predicted model showed a resonance at around 0.7, 0.8 gigahertz. And we understand why this happens. This occurs because the model accuracy depends very sensitively on the number of training iterations. Okay, so although your training data set reduces, you have to train your model a large number of times. So you have to iterate and iterate and iterate. And when we did this work, we were somewhat limited by the processing power that was available to us. So this is still work in progress. And we anticipate many more exciting results for the optics domain using this framework. Okay. So this is the work that we are going to present about 2 weeks from now at the Neural Information Processing Systems Conference. So it's very nice to see a lot of these optics and photonics motivated work get accepted at these sort of premier venues for computer sciences. So the two fields seem to be working closely together now. So this is my last slide, just to summarize. We know now that machine learning and deep learning based prediction and optimization tools are very useful for photonics. Okay, we've gone through several examples. They enable automation of design solutions. They are much faster than conventional methods. Once you've trained them, there is a one-time training cost involved here. And you can solve inverse problems to find, relationships between the design and the response spaces. And as I mentioned earlier, this is really what you need in real life. You know what kind of behavior the device should have. You don't necessarily know what the design of the device should be. So what is the future? The future is that now people have started to move on to, or they've proposed using higher dimensional data such as field profiles, vectorial field maps, etc., to predict performance. Not just simple reflection transmission intensity kind of values. You can increase the number of design variables, of course. So you can have more efficient models where this increase in the number of design variables will not add to your computational cost. And you can build on multi-scale physics-inspired models. One physics-inspired model I showed you just now, and you can do many more like that. So this opens up a very exciting area for future work. And with that, I end my talk.